Okay, so welcome back everyone to the main part of this talk. So we are very happy to welcome Helen Jenne from the University of Oregon, who will be talking to us about the combinatorics of the double dimer model.
Hi everyone. If you're just joining, welcome. And if you were here for part one, thanks for staying. Okay, so today I'm gonna start with some motivation from the dimer model. And then I'll state my main result, which is a recurrence that the tripartite double dimer configuration satisfies. I'll spend some time talking about some of the ideas that went into the proof. And I'll conclude with an application to a problem in enumerative geometry that's a joint work with Ben Young and Gautam Webb. So throughout this talk, G will be a finite edge-weighted bipartite planar graph. Should I define any of those words? Okay, then I'll keep going. So a dimer configuration, which is also called a perfect matching of such a graph, is a collection of edges that covers each vertex exactly once. So shown is a dimer configuration of a grid graph. And in the 1960s, Castellan showed how to enumerate dimer configurations. For bipartite planar graphs, he defined a matrix called the Castellan matrix that's basically a bipartite adjacency matrix with signs. So the rows are indexed by the black vertices and the columns by the white vertices, and the entry is the corresponding edge weight between two vertices if there is an edge, and if not, there's a zero. And some of the entries have signs. What Castellan proved is that you can choose the signs of the matrix entries in such a way that the determinant of the matrix is the sum of the weights of the perfect matchings of the graph, where the weight of a matching is the product of its edge weights. So this example has three perfect matchings, the three vertical edges x, y, and z, the vertical edge x and these two horizontal edges, and the vertical edge c and these two horizontal edges. And sure enough, the determinant of this matrix is that sum. Great. And so in 2004, Eric Kuo proved that the generating function for perfect matchings of a graph, which we'll denote ZDG, satisfies this nice recurrence. So what he showed is that if we have four vertices A, B, C, and D that appear in cyclic order on a face of the graph, and where A and C are both black and B and D are both white, then the following recursion holds. So the generating function for dimer configurations of G times the generating function for dimer configurations of G with those four vertices removed is equal to the sum of products of generating function of generating functions of dimer configurations of modifications of G as shown. So each of these terms on the right-hand side comes from deleting one black vertex and one white vertex in all possible ways. And he gave a really nice proof of this fact. What he showed is that if you superimpose a matching of G with a matching of G with those four vertices removed, then the resulting configuration that you get has to have come from exactly one term on the right-hand side of the equation. Alternatively, you can prove his theorem using this identity from linear algebra, which is called the Desnanot-Jacobi identity, or sometimes it's known as Dodgson condensation. So in this identity, M is a square matrix, and Mij denotes the matrix M with row I and column J removed. So the idea is that you can prove Kuo's theorem using this identity and the Castellan matrix. since the determinant of the Castellan matrix is the weighted sum of the perfect matchings of a graph. So the idea is that if you delete a row and a column from the Castellan matrix, then what you'll get is a Castellan matrix of the graph with a black vertex and a white vertex removed. But there's some like fiddling with the signs, and you have to be careful there. So that's why there's a minus sign here and a plus sign in Quo's theorem. So that's another way to prove Quo's theorem. And Quo's condensation has a number of applications. One that I want to mention and spend some time on is he used his techniques to give a new proof of a well-known formula that counts plane partitions. So, and one of the reasons I am going to spend some time talking about this application is plane partitions will come up again later in this talk when we talk about the application to the problem in enumerative geometry. So
there's been a question in the chat.
Yeah.
So Graham asks, does this mean I should be thinking of ZTG as the determinant of the Castellan matrix with variables in all the entries?
Yeah. What does he mean with variables in all the entries? Yeah, I mean, yes, that's what Castellan proved, is that ZDG is the determinant of the Castellan matrix, up to a sign.
Oh yeah, I think I just mean like when you had specific edge weights there, then the Castellan matrix looks like just like a, like if I were to plug in values for X and Y and Z, it would just give a certain number. But that I don't know what that generating function is actually defined as. So I was just checking to make sure I was understanding what that meant correctly. The Z D of G.
Oh yeah, it's the sum over all dimer configurations of the weight of the dimer configuration, which is the product of the edge weights.
Okay, and those are just like a variable for each edge, basically.
Yeah.
Okay, cool.
Planar could be a number or whatever. Yeah.
Okay, thanks.
Yeah, sure. Okay.
Another question from James Prop asking if there's a link to the slides.
No, I'm sorry. Yeah.
No worries. Maybe we'll add that in the future. That was a good suggestion.
Yeah, that's a good idea. Yeah, sorry about that. Okay, great. Okay, so plane partitions. So in some sense, a plane partition is a pile of boxes in a corner of a room where the room is the positive octave. Gravity is pulling the boxes in the -1, -1, -1 direction. More precisely, a plane partition is a finite array of positive integers that's non-increasing in rows and columns. And the way to get from the definition to the interpretation as a pile of boxes in a corner of a room is that, for example, this first row 5, 4, 4, 2 is represented by the picture in that there's a stack of 5 boxes and then a stack of 4 boxes and a stack of 4 boxes and a stack of 2 boxes. So that's a plane partition. And then so the question that's natural to ask is, how many ways are there to stack n boxes in, say, an infinitely large room? And it turns out that there's a really nice answer to this question in terms of generating functions. So in the early 1900s, Percy McMahon proved that if you Q count plane partitions, so that means that if you sum over all plane partitions, the quantity Q to the number of boxes in the plane partition, then you get this beautiful product formula. And a related question to the question, how many ways can you stack n boxes in just an infinitely large room, is how many ways can you stack n boxes in a room that has restrictions on the size, so a room with dimensions r by s by t. And again, we get this really nice product formula. And this is the formula that Quo gives an alternate proof of using his techniques. And then, so the connection between plane partitions and dimer configurations is the following. So whenever you have a plane partition inside of an R by S by T room, in this case, this is a plane partition inside like a 3 by 3 by 3 room, you can think of it as a rhombus tiling of a hexagonal region of triangles. So this is a tiling of this region. And whenever you have a tiling of a region, that's equivalent to a perfect matching of the dual graph of that region. So Quo uses his like graphical condensation technique to prove a recurrence about the number of, or the Q count for plane partitions. And then after he proves that recurrence, he uses induction to give an alternate proof of McMahon's formula. So that's just an example of an application of Quo's work. There are other applications of, for example, there's some nice applications to the theory of cluster algebras, but I don't have time to go into those today. But the thing that I'll be talking about mainly is my thesis work, which was an analog of Quo's theorem for double dimer configurations. And this work was motivated in part by the potential for applications, since Quo's work has some really nice applications. Great. So now we'll define a double dimer configuration. So again, G is a bipartite planar graph. And from here on out, all of our graphs are going to have a set of special vertices called nodes on the outer face. And then a double dimer configuration on a graph with a set of nodes that you've fixed is a subgraph of degree 2 at the internal vertices and degree 1 at the nodes, except for possibly having some doubled edges. Equivalently, it's a configuration of disjoint loops, which are just cycles of length greater than 2, doubled edges, and paths that connect the nodes in pairs. So for each double dimer configuration, you have a planar pairing of the nodes. And then the weight of a double dimer configuration is the product of its edge weights times 2 to the L, where L is the number of loops in the configuration. And this 2 to the L factor, it comes from the fact that whenever you have a double dimer configuration, you can decompose it into 2 dimer configurations, one on a graph with some subset of the nodes. In this case, it happens to be all of the nodes, and another on the graph with the rest of the nodes. But then there's 2 to the L ways to do this decomposition, because whenever you have a loop, you have a choice for how to partition the edges into the 2 dimer configurations. So that's a double dimer configuration. My analog for Quo's theorem is going to hold for a particular type of pairing called a tripartite pairing. So a pairing is tripartite if the nodes can be divided into at most 3 sets of consecutive nodes, so that no node is paired with a node in the same set. And the way we visualize a tripartite pairings is by coloring the sets of nodes. So the pairing on the left is tripartite because the nodes can be colored consecutively red, green, and blue, so that no node is paired with a node in the same color, of the same color. And the pairing on the right is not tripartite because if, say, we try to do this kind of coloring by, say, starting by coloring nodes 2 and 3 red, then when we get to node 4, we have to switch colors. And then since 5 is paired with 6, when we get to 6, we have to switch with colors again. And then when we get to 8, we have to switch colors again, so that in the end, 4 colors are required. And with this definition, it's fine for like 8 and 1 to be the same color. So I think I should pause here because I always manage to confuse at least someone with this definition. Are there any questions?
So one question in the chat that I think you just answered, asking if consecutive is a cyclic notion.
Yeah. Yeah. I should.
Can I ask a question about the previous slide? Sorry, I didn't want to interrupt while you were explaining this one. Can you say again what the 2 to the L choices were?
Oh,
There's different ways to decompose the double
oh
bond.
yeah. So right. So like here I have a loop. So I could either put these vertical edges in this dimer configuration, or I could have put them in this dimer configuration.
Oh, I see. So different, I see. The L depends on the actual particular configuration we're looking at.
Yes, yes, yeah.
Okay, yes.
Yeah, good point.
Thank you.
Yeah, yeah, sure. Okay.
And Sarah asks in the chat, what is the maximum number of vertices in one connected component?
Of the
In the triangle.
Tripartite.
Oh, maximum number of vertices.
Can you have any number of vertices? Like if you just have a long cycle, black, white, black, white, black, white, or black, white, yellow?
I don't think I understand. Could you repeat that?
I was just wondering, can you have any length connected component there?
Oh, yeah. Or like by connected component, do you mean in the subgraph, or do you mean like the...
In the subgraph that you have at most 3 colors.
Yeah, so you mean like, could I extend this
Yeah.
cycle? Yeah, I mean, if the graph was bigger, I'm sorry, I think I'm still a little bit confused.
I guess I'm just trying to understand that definition. So if the constraint is just that you have at most 3 colors, then like the one on the left, you could have all, you could do it a couple different ways. Like that one that's labeled red could be separated from its black and white and connected over to the others, right?
Well, this is something that can be sort of confusing. Is we have sort of 2 completely different colorings: the black-white coloring that comes from it being bipartite, and the red, green, and blue coloring that comes from the definition of the pairing.
Oh, okay. I was not getting that.
Oh, okay. Yeah, no, that's a great question asked. Yeah, so I think really I should have, instead of coloring for black and white, I should say shading or something. So yeah, the coloring that I'm talking about is just this coloring of the red, green, blue. Okay.
And James Prop asks in the chat, do tripartite pairings have a nice forbidden subpairing characterization?
Not that I know of. Yeah, I don't know. Okay, great. Any other questions? Okay, so then, great. So then something I wanted to point out about tripartite pairings is that if you have a set of nodes, and you color them red, green, and blue, that determines the node pairing. So this picture just represents that there could be any graph inside this circle, and I'm just trying to demonstrate something about the nodes. And this is because all the pairings in a double dimer configuration are always planar. So if I wanted to have a planar pairing with this node coloring, then 5 and 6 have to be paired, 10 and 11 have to be paired, and 1 and 14 have to be paired. And then similarly, like 2 and 13 have to be paired, 4 and 7 have to be paired, and so on. And so then 3 and 8 have to be paired. So whenever you have a red, green, and blue coloring of the nodes, you have a unique tripartite pairing. Okay. So now I have all the definitions I need to state the main result. Just a piece of notation. DD sigma is going to denote the weighted sum of all double dimer configurations with a particular planar pairing sigma. And so the notation in the theorem is a little bit messy, so I'm just going to go straight to an example. So what we have is we have a set of nodes. In this example, we have 8 nodes, and they're colored red, green, and blue. And we let sigma be the corresponding tripartite pairing in which like colors are not paired. So 1's paired with 8, 2 and 5, 3 and 4, and 7 and 6. And then like in Quo's theorem, we have 4 nodes that are appearing in a cyclic order. In this example, it's 1, 2, 5, and 8, with the condition that 1 and 5 are both black and 2 and 8 are both white. And we also have a condition that we want the set X, Y, W, the 4 nodes that we picked to contain one of each RGB color, but let's not worry about that too much right now. So then what the theorem says is that the weighted sum of all double dimer configurations with this node set on this graph times the weighted sum of all double dimer configurations on the same graph, but where 1, 2, 5, and 8 are no longer nodes. So now 1, 2, 5, and 8 are just vertices with multiplicity 2, is equal to the sum of products of generating functions for double dimer configurations, where again, like with Quo's theorem, each of these terms on the right-hand side comes from deleting one black node and one white node, like for instance, 1 and 8. And then the pairing is always the unique pairing in which like colors are not paired together. So that is the theorem statement. Are there any questions?
Yeah. So in what sense is that considered the same graph with a node with nodes deleted? I'm not really sure how the graphs are related.
So like, we're always considering, in this theorem, we're always considering double dimer configurations on the same graph that we fixed at the beginning, but just the node set is different in each of these terms. So like this is on the far left, we have a double dimer configuration on this grid graph with 8 nodes, but then the next term is a double dimer configuration on a grid graph with just 4 nodes.
I see.
Okay. Any other questions? Okay. So then this is actually something I wanted to mention is this is actually a corollary of a more general result where X, Y, W, and V can be any 4 nodes as long as 2 of them are black and 2 of them are white, but just these like additional like cyclic order assumptions make the signs really easy to understand. So like another version of this theorem where it's not cyclic order would maybe have a minus sign here instead of a plus. Okay. So unlike the proof of Quo's theorem, this is not going to be like a nice bijective proof. We're going to use the Desnanot-Jacobi identity with a matrix that counts tripartite double dimer configurations. But in order to do that, I first need some background. So Kenyon and Wilson initiated the study of the double dimer model when they showed how to compute the probability that a random double dimer configuration has a particular pairing of the nodes. So for instance, they showed the probability that a random double dimer configuration has pairing 1, 2, 3, 4, 5, 6 is proportional to this polynomial and these quantities xij that I'll define in a second. So I'm not going to define this quantity PR hat for a little while, but it's just the probability that a double dimer configuration has this node pairing times a ratio of dimer counts. So Kenyon and Wilson refer to it as like a normalized probability. And then here's another example of another one of their polynomials. And just the thing that I wanted to point out in this example is that when we have a graph with 8 nodes, each of the monomials has 4 terms instead of 3. Okay, so now I'm going to define xij, and I just wanted to warn you that this is where things maybe get a little bit technical. So xij is a ratio of dimer counts. It's the weighted sum of dimer configurations of this graph GBWIJ over the weighted sum of dimer configurations of this graph GBW. So GBW is a subgraph of G that contains the nodes that are black and odd or white and even. So in this example, G and GBW are just the same graph because 1 and 3 are black and 2 and 4 are white. But if, say, we had this graph, then to obtain GBW, we would delete nodes 2 and 3 because 2 is black and 3 is white. And then GBW 1, 2 contains the node 1, doesn't contain the node 1 because GBW does, and it does contain the node 2 because GBW doesn't. Does that make sense? So GBWIJ contains the node I if and only if it's not in GBW. And then just to give another example, GBW24 contains the node 2 because that's not in GBW, but it doesn't contain the node 4 because that is in GBW. And then the thing that I just want to point out with this example is there are more black vertices and white vertices. So this graph doesn't have any dimer configurations. So this quantity x24 would just be 0. So that's going to be true in general, that xij is 0 whenever I and j have the same parity. And then another thing I want to point out about their polynomials is that each term in their polynomials, it corresponds to an odd-even pairing. And what I mean by that is each monomial is a product of xij's, where each ij is a pair in some odd-even pairing. Right, so although we're only interested in the probability that a double dimer configuration has a particular planar pairing, the terms that show up in these polynomials correspond to just general odd-even pairings. And then maybe something you've noticed is that all of the examples I've shown, the nodes alternate black and white. And that's because at the beginning of their paper, Kenyon and Wilson make a simplifying assumption that all their nodes are either black and odd or white and even. And this ends up being a really important, and we'll come back to that later. And so Kenyon and Wilson proved that this quantity PR hat is always going to be an integer coefficient homogeneous polynomial in the quantities xij. But the thing that we really care about is that in the special case where sigma is a tripartite pairing, the quantity PR hat can be expressed as a determinant. So again, I'm just going to go straight to an example here. So we have here we have a tripartite pairing because the nodes can be colored red, green, and blue so that no node is paired with a node of the same color. And so Kenyon and Wilson's theorem says that PR hat is the determinant of a matrix whose rows are indexed by odd nodes and columns are indexed by even nodes. And the columns are in the order determined by the pairing. So since node 1 is paired with node 6 is in the first column. So you can always read the pairing across the diagonal of their matrix. And then the entries in the matrix are either xij or they're 0 if the corresponding nodes like 1 and 2 have the same RGB color. Great. Any questions about that or anything? Okay. And then so I hadn't defined what PR hat is, so I'm going to now. It's a probability that a random double dimer configuration has pairing sigma times this ratio of dimer counts. And what that works out to be is the generating function for double dimer configurations with a particular pairing sigma divided by this quantity ZD GBW squared. And so then if we recall the Desnanot-Jacobi identity from earlier, it should seem like we're basically almost done, right, with the proof of the theorem. The idea would be to use the Desnanot-Jacobi identity with Kenyon and Wilson's matrix, because removing row I and column J of their matrix would correspond to sort of like deleting 2 nodes from the node set. but and maybe then there's some fiddling around with the signs, so this minus turns into a plus, but it feels like we should be almost done. And so I'm going to illustrate what goes wrong with it with an example. So this is the example we saw earlier of the condensation theorem, and here's Kenyon and Wilson's matrix, where again the rows are the odd nodes, the columns are the even nodes, and you can read the pairing across the diagonal. And so if we wanted to prove this identity using the Desnanot-Jacobi identity in this matrix, we would delete rows and columns 1 and 3, because rows 1 and 3 correspond to nodes 1 and 5, and columns 1 and 3 correspond to 8 and 2. And then Kenyon and Wilson's theorem says that the determinant of the matrix is ZD sigma divided by this quantity ZD GBW squared. But we do have, 5 other terms in this equation. So let's look at the determinant of the matrix M with row 3 and column 3 removed. So what we need to show is that this is equal to the number of double dimer configurations on the node set where 2 and 5 are no longer nodes with this pairing, and divided by this ZDGBW squared factor. And now the issue is that we can't just apply Kenyon and Wilson's theorem because the nodes aren't numbered consecutively. So we might hope that we can fix this by renumbering the nodes. So now we have 6 nodes labeled 1 through 6. But then now this assumption that I mentioned earlier that Kenyon and Wilson made, that the nodes of the graph are always black and odd or white and even, that's where this comes into play. So 2 is black and 3 is white, so we can't just apply their theorem. We might hope to sort of fix that by adding dangling edges of weight 1, because double dimer configuration on this graph should be in bijection with double dimer configurations on this graph. And now we've fixed the issue that our nodes weren't black and odd or white and even. So then Kenyon and Wilson's theorem tells us that that the generating function for double dimer configurations on this modified graph G tilde with this node set is proportional to the determinant of this matrix. But here I've written X tilde because when we change the graph, we change we change all the matrix entries, since the matrix entries are dimer configurations on this graph. So in order to prove that the determinant of this matrix minor is counting what we want it to count, we have to show that the determinant of this matrix times ZDGBW squared is equal to the determinant of this matrix with these X tildes times ZDG tilde BW squared, which you can show. It's just like a really messy computation that involves a lot of algebra, and I don't mean like abstract algebra, I mean like college algebra, and the computations get worse and worse when you have when you increase the number of nodes on your graph. And so the observation this leads to is we really just need to lift this assumption from Kenyon and Wilson's work that the nodes of the graph are black and odd or white and even. So that leads me into the approach we took, right? So then maybe the next observation is that with Kenyon and Wilson's assumption that the nodes are black and odd or white and even, G is just equal to GBW, so these terms Xij are just ratios of dimer counts of Gij over dimer counts of G. And so maybe the correct thing to do is just to make these ratios of dimer counts our matrix entries. So we let Yij be this quantity Zd of Gij over Zd of G. And we define PR tilde to be sort of the same as their PR hat, except with their GBW replaced with a G. And then establish analogs of Kenyon and Wilson's results without their constraint on the node coloring. So just to give some examples, Kenyon and Wilson showed that their quantities PR hat were integer coefficient homogeneous polynomials in Xij, and our quantities PR tilde are integer coefficient homogeneous polynomials in these quantities Yij. Xij was equal to 0 when I and j were the same parity, which was the same as being the same color because of their assumption that nodes are black and odd or white and even, and our variables Yij are 0 when I and j are the same color. And just to give a few more examples, so each term in their polynomials corresponded to an odd-even pairing, and each term in our polynomials corresponds to a black-white pairing. So, right, so the idea behind this work was just to basically prove analogs of Kenyon and Wilson's theorem with the word odd-even replaced with the word black-white everywhere. And then what we found is that that assumption that the nodes be black and odd or white and even really simplified the signs a lot. And so when we removed that assumptions, things kind of exploded into a little bit of a disaster, which I'm going to illustrate with an example. So here's just an example of a lemma from Kenyon and Wilson's paper that ends up being pretty important. And it just says that whenever you have an odd-even pairing, the odd-even sign of that pairing, which I'll define in a second, times the product over all pairs in that pairing of this quantity -1 to the absolute value of I minus j minus 1 over 2, that you should just think of as being like the sign of a pair is equal to -1 to the number of crosses in that pairing. So we have to come up with a version of this for black-white pairings. And so the first thing is, well, how do we define this odd-even? How do they define this odd-even sign? The way the odd-even sign of a pairing is defined is just by thinking of it as a permutation one-line notation. So whenever you have an odd-even pairing, you can write the odd nodes in increasing order, and then the even nodes that they're paired with. And then the odd-even sign of that pairing is just obtained by dividing all of the even nodes by 2. And then it's the sign of this 312 considered as a permutation in one-line notation. And then you can define the sign of a black-white pairing really similarly. So if you have a black-white pairing, you can write the black nodes in increasing order and the white nodes that they're paired with, and then just subtract 4 from each of the white nodes, because this is a graph with 8 nodes, and then the black-white sign of the pairing is just the sign of the permutation 3, 4, 1, 2. Are there any questions? I saw some of the flashes.
Yep, Sarah Billy was asking why this sign calculation is a disaster.
Huh?
I asked, why are you calling it a disaster? Because it looks really nice to me, actually. It looks like the signs just collapsed down and it didn't end up being so bad. So what's the disaster?
Oh, well, that's what I'm showing with this example, sort of, is like that it is, I guess it's, the disaster was, I guess, having to like redefine all these signs is, right. So like this is really, I mean, this is really nice. Their lemma, just the disaster part was that it wasn't always like immediately obvious how to redefine the signs. So in this case, in this first example, it's really kind of clear what to do, how to define the sign of a black-white pairing. And the thing that I ended up having more trouble with was this other part of their lemma. So it wasn't, if you have a pair in an odd-even pairing, this exponent is always going to be an integer, but if it's a black-white pairing, it won't. And it just, for a really long time, just like wasn't obvious to me how to, if you have a pair in a black-white pairing, like I wasn't sure what to replace this with, basically.
Oh, I see. The disaster was in the generalization.
Yes, that's what I meant.
Yeah, okay, thank you.
Yeah, sure. Yeah, so, right, so that was the next task in trying to generalize this lemma, is what do we replace this exponent with? And it turns out that the thing to do is that if you have a pair in a black-white pairing, you should basically like keep track of the number of pairs of consecutive nodes that appear when you travel from I to J. So just to give an example, if I have a black-white pairing and a 7 and 3 are paired, then to compute the sign, I'll compute -1 to the absolute value of 7 minus 3, and then I'll add the number of pairs of consecutive nodes of the same color that appear between 7 and 3. So in this case, there's just the pair 4, 5, and then that'll be my sign. And then if I'm instead computing the sign of the pair 3, 8, then there are 2 pairs of consecutive nodes of the same color, 4 and 5, and 7 and 8. And so then I add 2 to that quantity, absolute value of I minus J minus 1. And so this, in Kenyon and Wilson's case, where the nodes always alternate black and white, our definition agrees with theirs. And you can check that this exponent is always going to be an integer. So then with that definition, then we get almost the same lemma, although we do end up getting a global sign that depends on the node coloring, which I don't have time to define today. And it's kind of, that was another thing that was sort of like hard to guess. But the point is that this is sort of what this process looked like, just trying to generalize their lemmas. There were lots of signs everywhere. But then the miracle is that when we got to the determinant formula, things started to really work out nicely. So just to remind you, this is Kenyon and Wilson's determinant formula. I've just rewritten it slightly differently. So they put their columns in an order that was determined by the pairing. And if you reorder them so that they're in ascending order, then you just get a global sign that's the same as the odd even sign of the pairing. And then my theorem, my determinant formula is just basically it looks very similar. The rows are indexed by black nodes and the columns by white nodes, rather than in Kenyon and Wilson's case where the rows were odd nodes and the columns were even nodes. And then once we have this determinant formula, then the proof method that we talked about earlier with the Desnanot-Jacobi identity works. So then you basically immediately get this theorem where X, Y, W, and V can be any 4 nodes as long as 2 are black and 2 are white. But of course you have a bunch of signs. And then in the special case where you assume that they appear in cyclic order so that they alternate black and white, then you can deduce that all the signs are positive. And so I have just a few minutes left, so I want to get to the application to the problem in enumerative geometry. So again, this is joint work with my advisor, Ben Young, and his other student, Gautam Webb. So this is an application to a problem in Donaldson-Thomas and Pandharipande-Thomas theory. And those are both branches of enumerative geometry. And I'm going to say basically as little about the geometry as possible because it's not something that I know much about. But my understanding is that both of these theories give frameworks for counting curves in a Calabi-Yau threefold X. And from each of these theories, we have a generating function. So we have this generating function from DT theory that counts subschemes of X. And we have a generating function from PT theory that counts stable pairs. And for deep geometric reasons, these two generating functions are equal up to a factor of McMahon. So this is the McMahon function that we saw earlier. That's the generating function for plane partitions. And the thing that's really cool is that both of these generating functions have box counting interpretations. So on the DT side, Malik, Nekrasov, Akunikov, and Pandharipande proved that the DT generating function is equal to the generating function for plane partitions with boundary conditions lambda, mu, and nu. And so what that means is that, remember earlier we talked about plane partitions being like stacking boxes in a corner of a room. And plane partitions with boundary conditions lambda, mu, and nu have a similar interpretation, only now our room has baseboards. So we have this infinite baseboard with shape lambda, and we have this infinite baseboard with shape mu and also with shape nu, and then we're stacking boxes on top of these baseboards. And so just like we could think of plane partitions as dimer configurations of that honeycomb graph, there's still a dimer interpretation of plane partitions with boundary conditions. And so here's a picture illustrating that, although note that these are not the same boundary conditions as are shown in the middle picture. So that's the DT interpretation. On the PT side, the box counting interpretation is conjectural. So it's conjectured that the PT generating function is the same for the generating function for these objects called labeled box configurations. And so with a labeled box configuration, you have this container where again, you have these like 3 infinite legs that are determined by the partitions. So here our partitions are just 2 and 1 and 1. And now gravity is pulling you in the opposite direction. And the rules for stacking boxes inside the container are really weird and hard to understand. So I'm not gonna get into it, especially as I only have a couple minutes left. But the punchline is that these labeled box configurations can be interpreted as double dimer configurations. And in particular, the double dimer configurations that you get from these labeled box configurations all have tripartite pairings. So our goal is to prove directly that the generating function for these plane partitions with boundary conditions is equal to the generating function for labeled box configurations up to this factor of McMahon. And the idea behind the proof is that the left-hand side has a dimer configuration interpretation, and the right-hand side has a double dimer configuration interpretation. And so then we know that both sides satisfy the same condensation recurrence. The left-hand side satisfies quo-condensation, and the right-hand side satisfies double dimer condensation. So that's the idea, although this is still a work in progress, and there are some details to work out there. And so that's all the time I have today, but thank you so much for listening and for coming to this talk. And I'll take any questions now.
Feel
Okay,
free
maybe.
to put something in the chat if you want in lieu of clapping. That always is nice.
Okay, maybe I should ask yet another question. Sorry. This is the first time I'm hearing you talk about it. Also, I've read a little bit about this. So now all of my questions are coming up that I never had anyone to ask. So from what I understand, non-intersecting lattice paths can be viewed as a dimer model. Is that right?
Yeah, that's true.
So where you split up a vertex into input, into entry and exit. So if you do that, what would the double dimers then correspond to?
Sorry, could you repeat that?
So if you have a directed graph and you make this construction where you split each vertex into entry and exits, and so non-intersecting lattice paths become dimers. What would the double dimers then be in terms of the original digraph? Is this something that comes up and that has another, that is known under another name?
I'm sorry, I still don't understand. Your question is about double dimer configurations and non-intersecting lattice paths.
So okay, let's see. So if I have if I have a directed graph and I turn it into a bipartite undirected graph by doubling each vertex, then the non-intersecting lattice paths become dimers, from what I understand. The question is, what becomes double dimers? Well, I mean, is there something that does?
I think there could be, but yeah, unfortunately, I just don't know the answer to your question. I think so. Yeah, I don't think I know that much about this directed graph turning it into a. I don't think I really know much about the construction you're describing. If there's maybe anyone else in the room that can help me out, feel free to chime in.
I mean, I know a person who could, but she left mess.
So. Okay. Great. Yeah.
Yeah. So regarding this question, I think so Thomas Lamb have this paper called Electroid Variety, blah blah blah, very long title, and it has some kind of construction like that.
Okay. What did you say the title was?
I'm not particularly sure if this is relevant. Electroid varieties.
If you can find it and put it in the chat, that might be helpful to everybody.
Oh, great! Somebody found it.
Oh, you guys are quick.
Oh, okay, great. Okay.
Well, assuming that's the one you meant.
Yes. And there's this construction that.
Okay. Okay, I'll have to look into that. Thank you for bringing that up.
You know, anybody who wants to can save the chat by just clicking on those three little dots at the bottom there. It's kind of a handy feature.
There's some construction that go from an electrical network to bipartite graphs, and probably that's what you meant. I'm not exactly sure.
I've got a question about the recurrence formula. I was wondering, so it looked like the thing that was being reduced kind of each step of the recurrence is the number of nodes, is that right?
Yeah.
So if you were to apply this repeatedly, would it reduce to the case of like computing this for a nodeless double dimer model, essentially?
Yeah, I think so.
Is that like easier in some sense? I guess it would be. It's fewer data to worry about or something.
I see. Yeah. So yeah, I haven't thought about that too much. I guess that would give you a way to like compute double dimer configurations, but I'm not sure that it would be faster than like Kenyon and Wilson's method for computing them.
Okay, cool. Thanks.
But yeah, but I think you're right that it would. So yeah, that's something I should think about that more. Thank you.
Mm-hmm.
Yeah.
Okay, well, if there are no more questions, let's thank Helen again.